Our universe is governed by a set of fundamental laws and constants, numbers that dictate everything from the strength of gravity to the charge of an electron. We have, for a long time, assumed that these values are simply random, a cosmic lottery that happened to produce the reality we see. But what if they are not? What if these numbers are so exquisitely and improbably perfect for the existence of life, so finely tuned on a razor's edge of possibility, that they suggest the universe itself is a purposefully calibrated instrument? This is the story of the cosmic blueprint, and the profound question of whether our universe was designed for us. This is an idea known as the fine-tuning argument. It is not an argument born of emotion or intuition, but one that has emerged from the very heart of modern physics and cosmology. As our understanding of the universe has deepened, we have come to realize that our existence depends on a delicate and seemingly impossible balance of the forces that govern all of reality. If any one of these fundamental values were changed, even by the tiniest, most infinitesimal amount, the result would be a universe that is sterile, chaotic, and dead. A universe without stars, without planets, and without us. Let us begin with the most familiar of the forces, gravity. It is the great patient sculptor of the cosmos, the force that pulls matter together to form stars and galaxies. But the strength of gravity, determined by a number known as the gravitational constant, is a value of breathtaking precision. If the force of gravity were just a tiny fraction stronger, the universe would not have been able to expand after the Big Bang. It would have collapsed back in on itself, a great cosmic recoil, long before the first star ever had a chance to ignite. Conversely, if the force of gravity were just a tiny fraction weaker, it would have been too feeble to ever pull matter together. The primordial gas of the early universe would have simply drifted apart forever, forming a thin, cold, and eternally empty void. There would be no galaxies, no stars, no planets. The fact that we have a universe of beautiful, complex structures is a direct result of gravity having the exact strength that it does. It is a force tuned for construction, not for collapse or for dispersion. An even more profound example of this fine-tuning lies deep within the heart of every atom. The strong nuclear force is the powerful glue that binds protons and neutrons together in the nucleus. Its strength is what allows for the existence of all the elements heavier than hydrogen. It is also the engine of the stars. In the core of a star, the strong force is what overcomes the immense electrical repulsion between protons, allowing them to fuse together and release the light and energy that powers the cosmos. But the precise value of the strong force is a miracle of balance. If it were just slightly weaker, by even 1%, protons could not stick together. The universe would be composed of nothing but hydrogen. There would be no helium, no carbon, no oxygen, no iron, no chemistry, no planets, no life. And if the strong force were just slightly stronger, by as little as 2%, the consequences would be just as catastrophic. Protons would stick together so easily that all the hydrogen in the early universe would have been fused into heavier elements almost immediately after the Big Bang. There would be no hydrogen left to serve as the long-lasting fuel for stars. The stars would never have switched on. The universe would be a dark, lifeless place, filled with inert, heavy elements. Our existence depends on the strong force being in an incredibly narrow, life-permitting window. Perhaps the most staggering and famous example of fine-tuning is a value known as the cosmological constant. This is a number that represents a kind of intrinsic energy of space itself, a force that is causing the expansion of the universe to accelerate. For decades, our best theories predicted that this value should be enormous, but when we measured it, we found a value that is almost zero. It is so small, so unbelievably close to nothing, that it is the most precisely measured, and the most poorly understood number in all of science. To describe its precision is almost impossible with words. It would be like throwing a dart from one side of the observable universe to the other, and hitting a bullseye just 1 millimeter wide. If the cosmological constant were even slightly larger, its repulsive force would have been so great that it would have ripped the universe apart before gravity ever had a chance to form galaxies. The universe would have been a thin, featureless, and rapidly expanding void. If it were a different value, a large negative number, its attractive force would have caused the universe to collapse in on itself with breathtaking speed. The fact that we live in a large, stable, long-lived universe, a universe that expands slowly enough to allow for the formation of structures, is a direct consequence of this number being tuned to a precision of 1 part in 10 to the power of 120, a number so improbable it defies all chance. The list of these cosmic coincidences goes on and on. The mass of the neutron is slightly heavier than the mass of the proton. If it were the other way around, all protons would have decayed into neutrons, and there would be no atoms. The strength of the electromagnetic force, the ratio of the mass of the electron to the proton, dozens of these fundamental, seemingly random numbers, all have to be exactly what they are, all working in perfect concert, to produce a universe that is not just stable, but is capable of producing the building blocks of life. This has led to a profound and deeply unsettling question in the heart of physics. Why? Why this specific set of numbers? Why this version of reality? One proposed answer is the anthropic principle. This idea suggests that we should not be surprised to find ourselves in a universe that is so perfectly suited for our existence. Because if the universe were any different, we would not be here to observe it in the first place. This principle comes in 2 forms. The weak version simply states that our observations are biased by the fact that we exist. It is a selection effect. There is no deeper meaning to it. We won the cosmic lottery, but the strong version of the principle is more provocative. It suggests that the universe in some way had to be the way it is in order to one day give rise to conscious observers who could perceive it. It hints at a deeper connection between the laws of physics and the existence of a mind. Another potential explanation is the idea of the multiverse. This theory proposes that our universe is not the only one, that there may be an infinite number of other universes, all existing in parallel, and each one of these universes has its own, randomly selected set of physical constants. Most of these universes would be sterile and dead, with their physical laws not permitting the formation of stars or complex matter. But with an infinite number of universes, it is inevitable that some, by pure chance, would have the perfect combination of laws to support life. We naturally find ourselves living in one of those lucky life-permitting universes. This is a powerful and elegant idea, but it is one for which we have no direct testable evidence. It is a hypothesis that currently lies at the very edge of science, in the realm of metaphysics. It answers the question of fine-tuning by proposing an unproven, and perhaps unprovable, infinity of other worlds. It does not explain why the blueprint of our own universe is so special. It simply says that our special blueprint is one of many. And so we are left with the evidence itself, a set of fundamental rules of precisely chosen numbers that seem to have been calibrated with breathtaking accuracy to make our existence possible. This does not prove that the universe was designed. Patterns do not in themselves prove purpose, but it is a pattern of such profound improbability, of such exquisite and life-giving order, that it resists easy dismissal. It is a pattern that invites us to wonder, to ask the deeper question: is the universe a magnificent and improbable accident, or is it a masterpiece? The delicate balance of the great universal constants sets the stage for a cosmos that can exist. But a universe that simply exists is not the same as a universe that can host life. For that, another, more intricate layer of fine-tuning appears to be necessary. The very laws of chemistry and nuclear physics, the rules that govern how matter interacts and transforms, seem to be written in a language that is profoundly biased towards the creation of complexity, stability, and the very building blocks of life itself. Consider the humble water molecule, two hydrogen atoms bonded to one oxygen atom. Its existence is a direct consequence of the laws of electromagnetism, but its behavior, the collection of strange and uniquely life-giving properties that it possesses, is a result of the exquisite fine-tuning of that same force. The strength of the electromagnetic force dictates the precise angle of the bond between the atoms, and this angle is the key to everything. Because of this specific angle, the water molecule is polar. It has a slightly positive end and a slightly negative end. This polarity is what allows water to be the universal solvent, to dissolve more substances than any other liquid, to carry the nutrients and minerals necessary for life through our oceans and through our own veins. It is what allows ice to float, an almost unique property among substances, which insulates the liquid water beneath and allows aquatic life to survive the winter. It is what gives water its high specific heat, its ability to absorb and store vast amounts of energy, which stabilizes our planet's climate. If the strength of electromagnetism was slightly different, the bond angle would change, and all of these life-giving properties would vanish. Water would become a simple, uninteresting, and biologically useless liquid. An even more profound and startling example of this fine-tuning lies in the heart of the stars. The story of our existence is the story of the element carbon. It is the backbone of every protein, every fat, every strand of DNA. It is the indispensable building block of all known life. But carbon does not just exist. It must be made, and the process by which the universe makes carbon is so specific, so improbable, that it has been called a put-up job. Stars produce energy by fusing lighter elements into heavier ones. The first step is to fuse hydrogen into helium. This is a relatively straightforward process, but the next step, getting from helium to carbon, is incredibly difficult. A carbon nucleus has 6 protons and 6 neutrons. The most direct way to make it would be to fuse 3 helium nuclei together, but the chances of 3 separate helium nuclei all colliding at the exact same instant are almost zero. The process must happen in 2 steps. First, 2 helium nuclei fuse to create a nucleus of beryllium-8, but this beryllium-8 is incredibly fantastically unstable. It decays back into 2 helium nuclei in less than a quadrillionth of a second. For carbon to be made, a 3rd helium nucleus must, by pure chance, strike that beryllium nucleus in that impossibly short window of time. Under normal circumstances, this would almost never happen. The universe should contain almost no carbon, and yet it is full of carbon. The reason is a miracle of nuclear physics. In the 1950s, the astronomer Fred Hoyle was studying this problem, and he realized that the only way for it to work is if the carbon-12 nucleus possesses a very specific and unknown property. It must have an excited energy level, a resonance, that perfectly and precisely matches the combined energy of the beryllium-8 and the incoming helium nucleus. This resonance would act like a gateway, a secret door, dramatically increasing the probability of the reaction taking place. Hoyle, convinced this must be true, urged the nuclear physicists of his day to look for this specific energy level in the carbon-12 nucleus, and to their astonishment, they found it, exactly where he predicted it would be. This is now known as the Hoyle state. It is a finely tuned property of the atomic nucleus, a quirk in the laws of physics, without which carbon, and therefore we, would not exist. It is as if the universe has a built-in ladder, a perfectly placed stepping stone, specifically designed to allow for the creation of the element upon which all life depends. This is not the end of the story. For life to exist, there must also be oxygen, for water, and for respiration. Oxygen is made in stars by adding another helium nucleus to carbon. But if the oxygen nucleus also had a convenient resonance, just like carbon, then all the newly made carbon would immediately be converted into oxygen. There would be no carbon left. The universe needs the carbon-making reaction to be efficient, but it needs the oxygen-making reaction to be inefficient, and that is exactly what we find. By another stunning coincidence of nuclear physics, the energy levels of oxygen are positioned in just such a way that the conversion of carbon into oxygen is slow and difficult. The system is perfectly tuned to produce both in the right amounts. The weak nuclear force, another of the four fundamental forces, is also exquisitely tuned for our existence. It is the force that governs the rate of nuclear reactions. Its precise value controls the rate at which our sun burns its hydrogen fuel. If the weak force was slightly stronger, the sun would have burned through all of its fuel billions of years ago, long before complex life had a chance to evolve on Earth. If it was slightly weaker, stars like our sun might never have ignited in the first place. The steady, reliable, 10 billion year lifespan of our star is a direct consequence of the precise weakness of this force. This same force is also crucial for the creation of the heavier elements. When a massive star dies, it explodes in a supernova. It is in the incredible heat and pressure of this explosion that all the elements heavier than iron are forged. The weak force governs this process. If it were a different strength, the supernova might not happen correctly. It might fizzle out, or it might collapse into a black hole without ejecting its precious newly forged elements out into the cosmos. The very fact that our planet is made of a rich diversity of heavy elements is a testament to the fine-tuning of the weak nuclear force. And finally, let us consider the overall shape and fate of the universe itself. The geometry of the cosmos is incredibly perfectly flat. This means that the total energy density of the universe, the sum of all its matter and energy, is almost exactly equal to the critical density that is needed to prevent it from either collapsing back in on itself or expanding so rapidly that it rips itself apart. To achieve this state of perfect flatness required an unbelievable degree of fine-tuning at the moment of the Big Bang. The initial energy density had to be set to a precision of 1 part in 10 to the power of 62. Any deviation from this, and the universe would have been a catastrophic failure. While the theory of cosmic inflation offers a potential explanation for how this flatness was achieved, the initial conditions that allowed inflation to happen in the first place are themselves a profound fine-tuning problem. So we are left with a universe whose very architecture, from the grand cosmic scale of its expansion, down to the secret resonant energy levels of the atomic nucleus, appears to be a conspiracy to produce stability, a conspiracy to produce complexity, a conspiracy to produce the necessary building blocks of life. The very laws of physics and chemistry seem to be written in a language that is profoundly biased in favor of existence. The blueprint appears to be universal, but a blueprint is not enough. You also need a safe place to build. Our journey now takes us from the laws that govern the entire cosmos to the specific, privileged and quiet neighborhood in our own galaxy that our world calls home. The universal blueprint, the finely tuned laws of physics and chemistry, provides the potential for life. But a blueprint is useless without a safe and stable place to build. Our own galaxy, the Milky Way, is a sprawling, majestic city of 400 billion stars. But like any great city, not all of its neighborhoods are safe. For a delicate and complex phenomenon like life to arise, to endure, and to evolve over billions of years, it requires a very specific, very privileged, and perhaps exceedingly rare location, a quiet, protected, and resource-rich place known as the Galactic Habitable Zone. To understand why our location is so special, we must first appreciate the true nature of our galaxy. The beautiful, serene pinwheel of light we see in photographs is a place of constant and often violent activity. It is a dynamic ecosystem. Stars are being born in the fiery collapse of great gas clouds. Massive, giant stars are dying in cataclysmic supernova explosions that can outshine a billion suns. And at its very heart, a supermassive black hole 4 million times the mass of our Sun reigns as the galaxy's gravitational anchor, a place of unimaginable power and intensity. The Milky Way is not a gentle river of light. It is a living, breathing, and often dangerous place. The inner regions of our galaxy, the bustling and brilliant downtown district, are a realm of pure chaos. The density of stars here is immense. Stars are packed together so tightly that their gravitational influence on each other is a constant disruptive force. A planet orbiting a star in this region would have its orbit constantly perturbed, stretched, and pulled by the close passage of other stars. Its climate would be a chaotic nightmare of instability. It would be a cosmic game of billiards, with planets as the unfortunate balls and no hope for the long-term stability that life requires. This inner region is also bathed in a lethal bath of radiation. The supermassive black hole at the center, Sagittarius A star, is a source of powerful X-rays and gamma rays, and the high concentration of massive stars means that the rate of supernova explosions is incredibly high. Any planet in this region would be repeatedly sterilized, its atmosphere stripped away, its surface scoured clean of any life by the intense high-energy radiation from these nearby cosmic bombs. The galactic core is a beautiful but deadly place. Life is impossible there. So one might assume that the safest place would be in the far outer suburbs of the galaxy, the quiet, dark, and lonely frontiers. But these regions have a different and equally fatal problem. They are barren. The building blocks of life and of rocky planets themselves are the heavy elements: carbon, oxygen, nitrogen, silicon, iron, all the elements heavier than hydrogen and helium. These elements are not made in the Big Bang. They are forged in the fiery hearts of stars, and they are distributed throughout the galaxy by supernova explosions. The outer regions of the Milky Way are dominated by ancient first-generation stars. They are metal-poor, meaning they are made of almost pure primordial hydrogen and helium. There has not been enough time, and not enough generations of stars to enrich this region with the heavy elements needed to build a world like ours. You cannot build a rocky, life-bearing planet out of just hydrogen and helium. The galactic outskirts are a great, sterile, and resource-poor desert. This leaves a narrow, precious, and life-permitting ring of real estate in between these two extremes. This is the Galactic Habitable Zone, a quiet, suburban circle, far enough from the violent radiation and gravitational chaos of the core, but close enough to the galactic center to have benefited from billions of years of stellar recycling. It is a region that is rich in the heavy elements needed to build planets like Earth, quiet enough to allow those planets to exist in peace for the immense spans of time that complex life needs to evolve. Our Sun and our Earth resides perfectly within this privileged life-sustaining ring. But the story of our special location goes even deeper than that. It is not just our neighborhood, but our specific street, our specific orbit around the galactic center that appears to be uniquely suited for our existence. Our sun moves on a particularly special path. It is a nearly perfect circular orbit, known as a galactic co-rotation orbit. This means that our solar system orbits the center of the Milky Way at almost the exact same speed as the galaxy's great, sweeping, spiral arms. This is a fact of profound and life-giving importance. The spiral arms are the galaxy's great stellar nurseries. They are waves of compressed gas and dust, where new stars are constantly being born, and because they are full of young, massive giant stars, they are also the primary location of the galaxy's most violent events, supernova explosions. The spiral arms are the dangerous industrial and constantly exploding factories of the galactic city. Because our sun's orbit keeps pace with these arms, we rarely, if ever, have to pass through them. We spend the vast majority of our multi-hundred-million-year orbit in the quiet, safe, and relatively empty space between the spiral arms. We are not traveling on the chaotic, dangerous downtown freeway of the galaxy. We are on a quiet, protected country lane. This orbit keeps us out of harm's way, protecting us from the frequent nearby supernovae that would otherwise have repeatedly sterilized our world. The cosmic laws are right. The cosmic building blocks are present. And now we see that the galactic neighborhood, and even the specific galactic orbit, appear to be just right as well. The location seems to be perfect, but even in the safest neighborhood in the entire galaxy, you still need a safe and stable house. Our journey of discovery now takes us from the grand sweeping scale of the Milky Way down to the specific and equally improbable, life-giving architecture of our own solar system, a system that appears to be uniquely, and perhaps purposefully, designed for our protection. The sheer fact of our existence within the narrow life-sustaining ring of the galaxy is a profound starting point, but the layers of our privileged placement do not stop there. The more we learn about the different types of galaxies and the environments within them, the more we come to realize that not all galaxies are created equal. The very character of the Milky Way itself appears to be a crucial ingredient in the recipe for a habitable world. Galaxies come in many forms. There are small, chaotic, irregular galaxies, often the sites of furious, disorganized star birth. There are the great, ancient, elliptical galaxies, vast spherical collections of old red stars whose star-forming days are long since over. They are quiet, but they are also largely barren of the freshly forged heavy elements needed for new rocky planets. And then there are the grand, stable spiral galaxies like our own. A large, well-ordered spiral galaxy like the Milky Way may be the ideal type of galaxy to host complex life over the long term. It is old enough to have gone through multiple generations of stars, ensuring that its interstellar medium is rich in the heavy elements, the raw materials for planets and biology, yet it is still young and dynamic enough to have ongoing active star formation in its spiral arms, allowing for new third-generation stars like our Sun to be born. It is a perfect balance of maturity and vitality, of resources and opportunity. Even among spiral galaxies, our Milky Way appears to have had a remarkably calm and stable history. Galaxies, like all things, are subject to the laws of gravity, and they frequently collide and merge with one another. Our own galaxy shows clear evidence of having consumed or eaten many smaller dwarf galaxies over the course of its long life, their stars now assimilated into our own halo. But the Milky Way has not experienced a major disruptive merger with another large galaxy for over 10 billion years. A merger with a galaxy of a similar size would be a catastrophic event on a galactic scale. The gravitational tidal forces would disrupt the stable, circular orbits of countless stars for flinging solar systems like our own into the dangerous inner regions or out into the barren void. The collision of the vast gas clouds from both galaxies would trigger a furious galaxy-wide burst of star formation, a starburst which would be followed by a wave of supernova explosions, bathing the entire galaxy in a sterilizing flood of lethal radiation. The long, quiet, peaceful period of stability that life on Earth has required would have been impossible. Our galaxy's quiet history is a key part of our own. Zooming in closer, we find that even our immediate, local, interstellar neighborhood is uniquely and improbably serene. Our solar system is currently moving through a region of space known as the local bubble. It is a vast peanut-shaped area of the interstellar medium, about 300 light-years across, in which the density of gas and dust is exceptionally, almost unnaturally, low. This bubble was likely carved out by a series of about 15 supernova explosions that occurred in a nearby star cluster between 10 and 20 million years ago. The combined force of these explosions swept our local region of the galaxy clean, blowing away the dense clouds of gas and dust. We are, in a sense, traveling through a great cosmic clearing in the interstellar forest. The protective nature of this bubble cannot be overstated. If our solar system were, at this moment, ploughing through one of the dense, giant molecular clouds that are common elsewhere in the galaxy, the consequences would be severe. The immense gravitational pull of the cloud could disrupt the orbits of the comets in our distant Oort cloud, sending a constant, deadly rain of impacts into the inner solar system. The dense gas and dust could also compress our sun's own protective magnetic bubble, the heliosphere, allowing more harmful cosmic rays to reach the Earth. We are, by a fortunate accident of cosmic timing, in a uniquely safe and empty patch of space. This is all a matter of luck, a convergence of improbabilities, the right kind of galaxy, a grand and stable spiral, the right kind of history for that galaxy, a long and peaceful one free of major collisions, the right kind of location within that galaxy, the quiet, resource-rich habitable zone, the right kind of orbit within that zone, a stable, circular path that keeps us out of the dangerous spiral arms, and finally the right kind of local weather, a temporary but long-lasting bubble of empty space that protects us from the hazards of the interstellar medium. The galactic stage, it seems, has been perfectly and precisely set through a series of what appears to be incredibly fortunate coincidences. Each one is a necessary, but not sufficient, condition for our existence. But this is only the second great layer of the design. The next layer brings us much closer to home. For even in the safest and most privileged location in the entire galaxy, a fragile, life-bearing world requires its own personal and equally improbable system of local guardians. Our journey now takes us from the scale of the galaxy and into the unique and life-sustaining architecture of our own solar system. Our journey has brought us from the finely tuned laws of the cosmos to our uniquely safe harbor within the Milky Way galaxy. The stage has been set on a galactic scale, in a quiet neighborhood, rich with the materials needed for life and protected from the worst of the cosmic violence. But this is not enough. Even in the safest neighborhood in the entire galaxy, a fragile, life-bearing world requires its own personal and equally improbable system of local guardians. We now turn our gaze inward to the unique and life-sustaining architecture of our own solar system. The story of any solar system begins with its star. The star is the heart, the engine, the source of all light and energy, and the nature of that star dictates the nature of every world that orbits it. Our Sun is a G-type main sequence star, a yellow dwarf, and it is, by every measure we have, the perfect kind of star for a world that intends to host complex, enduring life. This is not a trivial statement. The vast majority of stars in our galaxy are not like our Sun. Over 75% of them are red dwarfs. These are small, dim, and incredibly long-lived stars, but they are deeply problematic for life. Because they are so dim, their habitable zone, the Goldilocks region where liquid water can exist, is incredibly close to the star. A planet in this zone would be tidally locked, with one side perpetually baked in constant daylight and the other side frozen in an endless night. Furthermore, red dwarfs are notoriously violent, especially in their youth, prone to unleashing powerful, sterilizing flares that would strip away the atmosphere of any nearby planet. On the other end of the spectrum are the great, brilliant, blue giant stars. These are the titans of the cosmos, magnificent and incredibly powerful, but their great power comes at a great cost. They burn through their nuclear fuel with incredible speed, living for only a few million years before they die in a cataclysmic supernova explosion. This is not nearly enough time for the slow, patient, billion-year process of complex life to unfold. Our Sun, however, is a model of stability. It is in its quiet, serene middle age, its energy output remarkably consistent for billions of years. It is not too hot and not too dim. It is not prone to the violent, sterilizing flares of a red dwarf. And it has a lifespan of 10 billion years, a vast and peaceful stretch of time, more than enough for a planet to cool, for life to emerge, and for that life to evolve into something complex and conscious. The Sun is a Goldilocks star, a gentle and dependable furnace, a prerequisite for a designed world. But a perfect star is not enough. The inner solar system must also be protected from the constant rain of comets and asteroids that lurk in the outer darkness, and our solar system has a guardian, a colossal, silent protector that has been shielding the Earth for its entire existence. That guardian is the planet Jupiter. It is difficult to overstate the sheer scale of Jupiter. It is a world of almost unimaginable size and mass. It is more than twice as massive as all the other planets in our solar system combined. It is a gravitational tyrant, a great and powerful anchor that dictates the motion of everything around it. And its most important job for us is that of a cosmic bouncer. The outer solar system is filled with billions of comets and asteroids, icy and rocky remnants from the formation of the planets. Their orbits are often unstable, and many of them are on trajectories that would eventually send them hurtling into the inner solar system, on a collision course with Earth. But between them and us stands Jupiter. Its immense gravitational field acts as a giant shield, a cosmic vacuum cleaner. It absorbs many of these incoming projectiles, and it ejects countless others from the solar system entirely. We have seen this guardian in action. In 1994, the comet Shoemaker-Levy 9 was captured by Jupiter's gravity and torn apart. For a week, the fragments of this comet slammed into Jupiter's atmosphere, one after another, creating a string of impact scars, some of which were larger than the entire planet Earth. We watched from a safe distance as our great guardian took a series of bullets that would have caused a global, life-extinguishing extinction event had they struck our own world. Without the silent, constant protection of Jupiter, the Earth would have been subjected to a continuous and sterilizing bombardment. The long, stable peace required for complex life to evolve would have been impossible. The very architecture of our solar system also appears to be special. The planets of our system exist in a state of remarkable order. We have the small, rocky terrestrial worlds in the inner system, and the great, massive gas giants in the outer system. And crucially, all of them travel on stable, predictable, and nearly circular orbits. This orderly arrangement keeps the climate on Earth stable and predictable over long timescales. This is not the galactic norm, as we have begun to discover thousands of other solar systems around other stars. we have found that many of them are chaotic and violent places. A common configuration is the hot Jupiter, a gas giant that has migrated from the outer system into a close, scorching orbit around its star. In the process of this migration, such a giant planet would have destroyed or ejected any small, rocky, Earth-like worlds that may have been in its path. The fact that our own Jupiter has remained in a distant, stable orbit, acting as a protector rather than a destroyer, is another profound and perhaps improbable feature of our local design. The cosmic laws have been shown to be perfect. The galactic address has been revealed to be ideal. And now we see that the local neighborhood, with its gentle, stable sun and its great guardian planet, is a fortress of tranquility. The design appears to be layered, each level of reality providing the necessary stability for the next. Our journey now takes us to the final and most intimate layer of this structure. We move from the architecture of the solar system to the unique and perhaps unrepeatable features of our own world, the rare Earth, the unique stability of our Sun, and the profound protective influence of our great guardian planet, Jupiter, are two of the foundational pillars of our solar system's life-sustaining design. But the architecture of our home is more complex and more elegant than just these two elements. The very way our solar system is laid out, the neat and orderly division of its worlds, is a consequence of another crucial feature that appears to be finely tuned for the emergence of a world like ours. This feature is known as the frost line. In the early days of the solar system, the Sun was surrounded by a vast rotating disk of gas and dust, the protoplanetary disk. Within this disk, a steep temperature gradient existed. It was incredibly hot near the young central Sun, and grew progressively colder as one moved outwards. The frost line was a specific distance from the Sun, a kind of thermal cliff where the temperature dropped enough for volatile compounds like water, methane, and ammonia to condense into solid ice grains. This simple dividing line had profound and lasting consequences for the formation of every planet. Inside the frost line, in the hot, inner regions of the solar system, only materials with a high condensation temperature could form solid particles. These were the heavy elements, the metals like iron and nickel, and the rocky silicate minerals. But these materials were incredibly rare in the protoplanetary disk, making up less than 1% of its total mass. As a result, the planets that formed here, Mercury, Venus, Earth, and Mars, are small, dense, and rocky. There simply was not enough solid material available to build anything larger. But outside the frost line, in the cold outer regions of the solar system, the story was completely different. In addition to the rare rock and metal, the vast and abundant reserves of water, methane, and ammonia ice could also condense into solid particles. This meant there was far more solid material available for building planets. The cores of the outer planets were able to grow much larger and much faster than their rocky siblings in the inner system. Once these cores reached a critical mass, their gravity became so powerful that they were able to sweep up and hold on to the most abundant material of all, the hydrogen and helium gas that made up the vast majority of the disk. This is how the great gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune, were born. This elegant natural sorting mechanism, a direct consequence of the laws of temperature and chemistry, is what created the beautiful and orderly architecture of our solar system. The neat division between the small rocky inner worlds and the colossal gaseous outer worlds is not a coincidence. It is a predictable outcome of the frost line. And the Earth's position just inside this line appears to be particularly advantageous. It allowed our world to form as a rocky terrestrial planet, but one that was close enough to the great reservoir of water ice in the outer system to acquire its oceans later through the delivery of comets and asteroids that were nudged into its path. Jupiter's role as the great guardian is paramount, but it does not act alone. The other giant planets are crucial parts of this system of protection. Saturn, the second largest planet, with its immense gravity, plays a vital role in stabilizing the orbit of Jupiter itself. Without Saturn's gravitational influence, Jupiter might have slowly migrated inwards over the eons, a hot Jupiter that would have wrecked the inner solar system. Saturn is the deputy guardian, a crucial partner in the gravitational dance that keeps our neighborhood safe. Further out, the ice giants, Uranus and Neptune, act as the great shepherds of the Kuiper Belt. This is a vast donut-shaped ring of trillions of icy comets that orbits the Sun beyond Neptune. The immense gravity of Uranus and Neptune sculpts the orbits of these icy bodies, keeping most of them locked in a stable, distant configuration. They prevent a constant, chaotic flood of comets from pouring into the inner solar system. The outer giants are the keepers of the gate, ensuring that the great icy wilderness of the outer system stays where it belongs. The asteroid belt, that great rocky river between Mars and Jupiter, also tells a story of this architecture. It is not, as was once thought, the remains of a single, destroyed planet. It is, in fact, a planet that was never allowed to be born. The planetesimals in this region were constantly stirred and gravitationally harassed by the immense, nearby presence of Jupiter. They were never able to coalesce into a single large world. The asteroid belt is a fossil, a visible and permanent record of Jupiter's immense power to shape the very structure of the solar system. And at the farthest, coldest, and darkest edges of our solar system lie two vast and mysterious reservoirs of primordial material. The Kuiper Belt, the donut-shaped home of the dwarf planets and comets, and even beyond that, the Oort cloud, a vast spherical, all-encompassing shell of perhaps 1 trillion comets, extending almost a light-year out into the interstellar dark. These two great reservoirs play a fascinating and dual role in the story of a designed Earth. They are, at once, the greatest threat to our existence, and the likely source of the very water that fills our oceans and the organic molecules that form the basis of life. They are the source of both the poison and the antidote. The beautiful, intricate architecture of our solar system, with its team of great, guardian, gas giant planets, acts as a perfect and sophisticated filtering mechanism. It is a system that largely protects us from the constant threat of a deadly cometary bombardment, while at the same time, in the early days of the solar system, it allowed just enough of these icy bodies through to deliver the precious, life-giving cargo of water and carbon to the young Earth's surface. It is a system of profound and life-sustaining order, a stable, long-lived star, a team of great guardian planets that protect the inner system and sculpt the outer, and a series of vast, icy reservoirs, all held in a delicate, long-term and life-permitting gravitational balance. The architecture of our solar system appears to be a near-perfect machine for protecting and nurturing a single, precious, rocky world. Our journey now takes us to that world itself, to the final and most intricate layer of the design. The Earth, the universal laws of the cosmos, appear to be finely tuned for existence. The galactic address of our solar system is an ideal and privileged one, and the local architecture of our Sun and its planets is a fortress of profound stability. Now we arrive at the very heart of the matter, the jewel within this cosmic clockwork. We turn our gaze to the specific, the unique, and the perhaps unrepeatable features of the Earth itself, a world that appears to be not just lucky, but exquisitely tailored for the emergence and endurance of complex life. The story of our rare Earth begins with its closest companion, a celestial body so familiar But we often forget how strange and how important it is. Our moon, it is not just a beautiful light in the night sky. It is the great stabilizer, the tidal engine, and the silent guardian of our world's long-term habitability. And its very existence is the result of a cosmic event of almost impossible violence and precision. The leading theory for the moon's origin is known as the giant impact hypothesis. It proposes that in the chaotic early days of the solar system, when the planets were still forming, a protoplanet about the size of Mars, which we have named Theia, slammed into the young molten Earth. This was not a direct, head-on collision that would have shattered our world, but a precise, glancing blow. The impact was still an event of unimaginable power, vaporizing the outer layers of both bodies and sending a colossal cloud of molten rock and debris into orbit around the Earth. Over thousands of years, the relentless pull of gravity gathered this orbiting debris together. It coalesced, cooled, and formed into the single large spherical body that we now know as our moon. But for this to have happened, the conditions had to be perfect. The size of the impacting body, the angle of the collision, the speed of the impact, all of these factors had to be within an incredibly narrow window. A little more speed, a slightly different angle, a larger or smaller impactor, and the result could have been two shattered planets, a chaotic ring of debris, or no moon at all. It was a cosmic trick shot of the highest order, and the gifts that this cataclysm bestowed upon our world are profound. The most important of these is stability. The Earth spins on a tilted axis, which is what gives us our seasons, but this tilt, left to its own devices, would wobble chaotically over geological time, pulled by the gravity of the Sun and the other planets. Without the Moon, the Earth's tilt could swing from 0 degrees to as much as 85 degrees. This would cause catastrophic and unpredictable swings in our climate. The poles could melt, the equator could freeze, and the seasons as we know them would vanish, replaced by an age of environmental chaos that would make the evolution of complex life almost impossible. But the immense gravitational pull of our large, close moon acts as a gyroscope, as an anchor. It holds the Earth's axial tilt in a steady, stable range between 22 and 24.5 degrees. This is what gives our world its predictable, reliable, and life-sustaining rhythm of the seasons. The moon is the great pendulum that keeps our planet's climate clock ticking on a steady and predictable beat. The moon's gravity is also the engine of our tides. The twice-daily rise and fall of the oceans creates a vast and dynamic ecosystem at the coastlines, the intertidal zone. This region, with its constant wet-dry cycles and its rich concentration of chemicals, is one of the leading candidates for the very origin of life itself, a perfect natural laboratory for the first complex chemical reactions to take place. And over the eons, the tidal friction created by the moon has been slowly breaking the Earth's rotation. In the deep past, a day on Earth was perhaps only 6 hours long. This frantic spin would have created winds of incredible violence and a much more chaotic climate. The moon has acted as a gentle brake, slowing our day to the stable, 24-hour period we now have, contributing to a calmer and more moderate climate. Statistically, a large moon like ours is a rarity for a rocky terrestrial planet. It is another profound anomaly, another piece of the puzzle that seems to fit a little too perfectly. But the design of our world is not just in its companion, it is in its very heart. Deep in the center of the Earth is a core of molten iron, churning and swirling as our planet rotates. This great, spinning, liquid metal engine is a geodynamo, and it generates the powerful magnetic field that surrounds our planet. This magnetosphere is our invisible, and most important, shield. It is the force field that protects us. and our atmosphere from the constant, sterilizing blast of the solar wind. We need only look at the fate of Mars, a planet that lost its magnetic shield and had its atmosphere and oceans stripped away into space, to understand how precious and essential this invisible guardian truly is. The same internal heat engine that powers our magnetic shield also drives another, uniquely terrestrial process, plate tectonics. The Earth's crust is not a single solid shell. It is broken into a series of great interlocking plates that float and move upon the semi-molten mantle beneath. This constant slow-motion dance of the continents is the key to our planet's long-term climate stability. This process acts as a global thermostat through what is known as the carbon silicate cycle. Volcanoes, driven by the movement of the plates, release carbon dioxide into the atmosphere, which warms the planet. At the same time, rainfall weathers the silicate rocks on the continents, a process which pulls carbon dioxide out of the atmosphere and locks it into carbonate minerals on the seafloor. The tectonic plates then slowly carry these minerals back into the Earth's mantle, where the carbon is eventually re-released by volcanoes, completing the cycle. This is a planetary-scale, self-regulating feedback loop that has kept the Earth's climate in a stable, life-permitting range for billions of years, despite the changing brightness of the sun and other cosmic factors. It is a feature that may be incredibly rare, and it is perhaps the single most important reason why our world has remained a paradise, while its siblings have not. The physical stage appears to be perfect in every conceivable way: a universe with the right laws, a galaxy with the right location, a solar system with the right architecture, and now a planet with the right size, the right moon, the right core, the right crust, and the right ingredients. Our journey now takes us to the final and most mysterious element of the design, the very phenomenon of life itself, and the improbable rise of a mind that can comprehend it all. The remarkable partnership between the Earth and its moon, and the unwavering protection of our planet's internal heat engine, are two of the most profound features that elevate our world from a simple rock into a potential cradle for life. But the design of our world is woven even more deeply into its very substance, the specific balance of the materials that make up our planet, the precise amount of water, the specific composition of our air. All of these are factors that, on their own, appear to be just as improbable and just as essential as our place in the cosmos. Let us begin with the most vital ingredient of all: water. Our planet is famously a blue world, a world of vast and deep oceans that cover over 70% of its surface. But the great miracle of Earth may not be that it has so much water, but that it has so little. This seems like a contradiction, but it is a point of profound importance. If the Earth had formed with, or had later acquired, significantly more water, the continents we know would not exist. The entire planet would be a global ocean, a water world with the deepest trenches of our current seas being the new surface. A world without continents would be a world without one of the most crucial mechanisms for long-term climate stability: the carbon silicate cycle, the great planetary thermostat that has kept our climate in a habitable range for billions of years, requires the weathering of exposed silicate rock on land. Without continents, this cycle would not exist. The planet's climate would be at the mercy of the slowly brightening sun, with no long-term mechanism to regulate itself. It would be a world prone to freezing over entirely, or to boiling away into a runaway greenhouse state. Conversely, if the Earth had significantly less water, it would be a desert world, a planet of vast, dry continents with only a few scattered seas. While life might arise in those seas, it would be unable to conquer the land. The global biosphere would be a fraction of its current size, and the climate would be much harsher and more extreme. Earth exists on a razor's edge, a knife's point of perfect balance between being a sterile water world and a barren desert world. It has just enough water to support a vast global biosphere and a stable climate, but just little enough to allow for the great continental landmasses that are the key to its long-term survival. The atmosphere of our world is another element of this delicate balance. Its very composition is a profound anomaly. It is a mixture of gases, primarily nitrogen and oxygen, that is in a state of extreme chemical disequilibrium. Oxygen is a highly reactive gas. Left to its own devices, it would quickly react with the rocks and minerals of the Earth's surface and be scrubbed from the air. The fact that our atmosphere is 21% free oxygen is a constant ongoing miracle. It is a sign that something is actively and continuously pumping this reactive gas into the system. That something, of course, is life itself. But the atmosphere's design is more subtle still. It has the property of being transparent to the specific wavelengths of light that the sun produces most abundantly, the visible spectrum. This is the light that the chlorophyll in plants is specifically designed to use for photosynthesis, the process that powers almost our entire biosphere. At the same time, the atmosphere is largely opaque to the most harmful forms of radiation coming from the sun, the high-energy X-rays and ultraviolet light. The ozone layer in particular is a perfect and specific shield against the very wavelengths of UV light that are most damaging to DNA. It is a spectral window, a filter that lets in the good light and keeps out the bad. This is another profound coincidence that makes complex life on the surface of our planet possible. The very size of our world is another factor in this perfect balance. Its mass, and therefore its gravity, is strong enough to hold onto its atmosphere and its oceans, preventing them from being blown away by the solar wind, the fate that befell the smaller Mars. But its gravity is not so strong that it was able to hold on to a thick, crushing primordial atmosphere of hydrogen and helium from the solar nebula. If the Earth were much larger, a super-Earth, it would have become a mini Neptune, a world with a vast, deep, and uninhabitable atmosphere of hydrogen and helium. Its size is in a perfect sweet spot, the ideal mass range for a large, rocky terrestrial world that can maintain a long-lived geological engine and a life-sustaining atmosphere, but without becoming a gas giant. It is a world of perfect balances, the right size and mass, the right and profoundly unlikely companion in its moon, the right internal engine to power its magnetic shield and its climate-regulating tectonics, the right amount of water, the right kind of atmosphere. Each of these is a necessary condition for our existence. For all of them to be true of a single planet, at the same time, in the same location, is a convergence of improbabilities so profound that it is difficult to accept as mere chance. The physical stage, down to the last and most subtle detail, appears to be complete, but a stage, no matter how perfect, is empty without an actor. Our journey now takes us to the final and most mysterious element of the design, the actor itself, the phenomenon of life. We have journeyed through the great nested layers of a seemingly perfect physical design, a universe with the right laws, a galaxy with the right location, a solar system with the right architecture, and a planet with every necessary physical and chemical ingredient for life. The stage is set. It is a masterpiece of stability and potential. But a stage, no matter how perfect, is empty without an actor. Our journey now takes us to the final and most mysterious element of the design, the actor itself, the phenomenon of life. The deepest and most profound mystery in all of science is the origin of life itself, the great unbridged canyon that separates the world of chemistry from the world of biology. We have the raw materials in abundance, the carbon, the hydrogen, the nitrogen, the oxygen, all present in the warm primordial oceans of the young Earth. We can even, in our laboratories, simulate the conditions of the early Earth and with a spark of energy, create the simple building blocks of life, like amino acids. But this is where the clear, easy path of explanation ends. A living cell, even the simplest bacterium we can imagine, is a machine of breathtaking complexity. It is a microscopic fortress, with a sophisticated, semi-permeable membrane that acts as its walls and its gates, controlling everything that comes in and goes out. Inside, it has a power plant, a metabolic engine that takes in nutrients and converts them into energy with incredible efficiency. It has a transportation network, a waste disposal system, and a set of instructions. And it is in this set of instructions that the true mystery lies. The transition from a collection of lifeless organic molecules to a single, living, self-replicating organism is not a simple chemical step. It is a leap from hardware to software. It is the emergence of information. A living cell is not just matter. It is matter that is organized by a complex digital code, a genetic blueprint. And the origin of this information, of this biological software, is a mystery for which we have no complete answer. The medium for this code is the DNA molecule, a structure of profound elegance and almost unimaginable efficiency. It is a digital four-letter alphabet, the famous A, C, T, and G. This chemical code stores the complete set of instructions for building and operating an entire organism. The information density of DNA is a marvel that dwarfs our own technology. A single gram of DNA can theoretically store more information than 1 trillion CDs. Every cell in your body contains a library of information so vast it would take a lifetime to read. But this is not just a passive library. The genetic system is an active information processing machine. It is equipped with incredibly sophisticated, built-in error checking and repair mechanisms. As the DNA molecule is copied during cell division, molecular machines scan the new strand, looking for mistakes, for typos in the code. When an error is found, these machines can snip out the incorrect letter and replace it with the correct one. It is a system of quality control so precise that it allows for the faithful replication of billions of letters of code, with only a handful of mistakes. This is not the hallmark of a random, chaotic system. It is the hallmark of a robust and elegantly designed information storage system. And this genetic language, this operating system for life, is universal. The same 4 letters, the same genetic code, the same basic machinery for reading and translating that code is used by every single living thing on Earth, from the bacteria in the deepest ocean trench to the tallest redwood tree, to you. It is a single, coherent, and universal language. This points to a common ancestor, a single origin for all life. But it also deepens the mystery of that origin. We are faced with a profound chicken and egg paradox. The DNA molecule holds the blueprint for building proteins, the molecular machines that do all the work in a cell. But to read the DNA blueprint and to build those proteins, the cell needs other, pre-existing proteins called enzymes. Furthermore, to copy the DNA molecule itself, the cell needs yet another set of incredibly complex protein machines. So which came first, the blueprint or the machines needed to read and build the blueprint? The DNA or the proteins? You cannot have one without the other. This suggests that the basic system of life, this intricate dance of information and machinery, had to come into being as a complete integrated whole. This brings us to one of the great puzzles of the fossil record, the Cambrian explosion. For over 3 billion years, life on Earth was simple, mostly single-celled organisms. And then, in a geological blink of an eye, about 540 million years ago, the fossil record shows the sudden, and spectacular appearance of nearly every major animal body plan that exists today. It was a biological Big Bang, an explosion of complexity and diversity. In this period, life developed shells and exoskeletons and limbs and digestive systems and circulatory systems, and most remarkably, the first sophisticated eyes. It was not just an increase in the number of species, it was an increase in the amount of biological information. A host of new complex architectural blueprints seems to have appeared, almost out of nowhere, with few, if any, clear ancestors in the preceding rock layers. The slow, gradual, step-by-step process of evolution seems to have been, for a time, suspended, replaced by a sudden and breathtaking burst of pure creative energy. And the final, and most improbable, step in this long and mysterious journey is the emergence of a mind. The rise of consciousness, the evolution of a brain, a 3-pound universe of neurons and synapses that is capable of not just reacting to the world, but of understanding it. An organ that can comprehend the mathematical laws that govern the cosmos, that can appreciate beauty in art and in nature, that can feel love, and that can ask questions about its own existence. Is it plausible that a blind, unguided process of random mutation and natural selection, a process aimed only at immediate survival, could produce a creature that writes poetry, that composes symphonies, that builds radio telescopes to look back at the beginning of time, and that wonders if its own world was designed? The outcome, a conscious mind that can perceive and appreciate the universe, seems to be a phenomenon of a completely different order than the proposed mechanism that created it. The physical universe appears to be finely tuned for life. The Earth appears to be a perfectly prepared stage, and now, life itself, in its profound complexity, its information-rich code, and its unbelievable culmination in a conscious, self-aware mind, appears to be the most improbable and finely tuned phenomenon of all. We are left with a final, overarching question. Given this staggering tower of seeming coincidences, from the fine-tuning of the cosmos to the firing of the neurons in a human brain, what does it all mean? What is the ultimate message of the great silence in a universe that seems so perfectly and so elegantly designed for a voice? The mystery of life is not just in its origin, but in its ongoing moment-to-moment operation. To truly appreciate the depth of the biological blueprint, we must journey inward, past the scale of organisms and ecosystems, and into the universe of a single cell. For it is here, in this microscopic and bustling metropolis, that we find a level of sophisticated, miniaturized, and perfectly integrated technology that rivals anything created by the human mind. Let us consider the common analogy of the cell as a great and busy city. The outer boundary of this city is the cell membrane. It is not a simple static wall, but a smart border, a fluid and flexible barrier with gates, pumps, and sensors that actively and intelligently control everything that crosses into and out of the city. It is a security system and a transportation network all in one, constantly monitoring the outside world and managing the flow of resources. The power for this entire operation comes from the city's power plants, the mitochondria. These are tiny bean-shaped organelles that take in the simple sugars and fats delivered to the cell and, through a complex multi-stage chemical reaction, burn them with oxygen to produce a small high-energy molecule called ATP. ATP is the universal energy currency of all life on Earth. It is the rechargeable battery that powers every single action in the cell, from copying DNA to contracting a muscle. And the mitochondria are masters of energy production, operating with a level of efficiency that our own best power plants can only dream of. The blueprints for the entire city are stored in the central library, the nucleus, encoded in the long coiled strands of DNA. When a specific tool or structural component is needed, a message is sent out. A copy of a specific gene, a single blueprint, is made in the form of messenger RNA. This messenger then travels out of the nucleus and to the city's factories, the ribosomes. The ribosomes are the 3D printers of the cell. They are complex molecular machines that read the messenger RNA transcript, letter by letter, and assemble a new protein, amino acid by amino acid, according to the precise instructions in the code. They work with incredible speed and almost perfect accuracy, churning out the thousands of different proteins that are needed to build, maintain, and operate the entire cellular city. Once these new proteins are built, they are sent to the city's post office and shipping department, a network of folded membranes called the endoplasmic reticulum and the Golgi apparatus. Here, the proteins are modified, folded into their final functional shapes, packaged and tagged with a chemical address label. They are then shipped out on the cellular highway system, a network of protein filaments called the cytoskeleton, to be delivered to the exact location in the cell where they are needed. This entire process, from the reading of the blueprint to the final delivery of the finished product, is a perfectly coordinated, automated, and self-sustaining system of manufacturing. A single human cell at any given moment is performing millions of these actions, a silent, microscopic, and perfectly ordered symphony of molecular machinery. But the true wonder lies deeper still in the nature of the proteins themselves. A protein is a long linear chain of amino acids, like a string of different colored beads. But it is not the chain itself that performs a function. For a protein to work, it must fold itself into a precise, unique, and incredibly complex three-dimensional shape. This is the great mystery of protein folding. The paradox is a profound one. An average-sized protein has a virtually infinite number of ways that it could fold. If it were to try and find its correct functional shape by random trial and error, it would take longer than the age of the universe to succeed. This is known as Levinthal's paradox. And yet, in the real world, inside the cell, a newly made protein snaps into its perfect, functional, three-dimensional shape in a fraction of a second. This means that the one-dimensional linear code of the DNA does not just specify the sequence of the protein, it also contains, in a way we still do not fully understand, the complex, three-dimensional, architectural instructions for its final folded form. The information is layered, one dimension dictating the form of the next. It is a stunning example of emergent, pre-programmed complexity, a process that seems less like random chemistry and more like a form of microscopic, high-speed origami. And at the very base of our entire biosphere, we find another system of almost unbelievable elegance and efficiency, the process of photosynthesis in the leaves of every plant, in every microscopic alga in the ocean, are tiny molecular engines called chloroplasts, and inside them the chlorophyll molecule acts as a perfect microscopic antenna tuned to the exact wavelengths of light that our sun emits most powerfully. When a photon of sunlight strikes a chlorophyll molecule, its energy is captured and, through a process that involves quantum mechanics, is transferred with almost 100% efficiency through a series of other molecules. This energy is then used to split a water molecule and to power the creation of the sugars that are the foundational fuel for almost all life on Earth. It is a process that takes light, water, and air and turns them into life. It is a form of natural quantum-level solar power that is far more sophisticated and efficient than any technology we have ever created. From the digital code of DNA to the quantum efficiency of photosynthesis, from the profound paradox of protein folding to the bustling, coordinated industry of a single living cell, The phenomenon of life appears to be a system of irreducible complexity and profound, information-rich design. The actor on our planetary stage is a miracle of engineering. This forces us to our final and most overarching question. If the universe is a perfect blueprint, and the Earth is a perfect stage, and life itself is a perfect actor, then why the silence? Why would a stage so perfectly set for a voice be met with the sound of an empty and quiet auditorium? The cosmic blueprint appears to be perfect. The galactic neighborhood seems ideal. The solar system is a fortress of stability. The Earth is a rare and precious jewel, and life itself, in all its information-rich complexity, is a masterpiece of biological engineering that has culminated in a conscious mind. Every layer of creation, from the moment of the Big Bang to the firing of the neurons in a human brain, seems to be a preparation for a great voice, for a mind to emerge and to speak, to call out into the cosmos and announce its presence. And yet, when we do just that, when we turn our great radio telescopes to the heavens and listen with all of our technological might, we are met with a silence so profound, so absolute, and so universal that it is perhaps the most significant and unsettling of all the data we have ever collected. This is the great and enduring mystery known as the Fermi paradox. The logic of the paradox is as simple as it is powerful. Our universe is ancient, over 13 billion years old. Our galaxy is home to hundreds of billions of stars and billions of potentially habitable, Earth-like planets. The laws of chemistry and biology that gave rise to us are the same laws that operate everywhere. Given the sheer number of opportunities and the immense spans of time involved, the galaxy should be teeming with other intelligent, technological civilizations. Many of them should be millions or even billions of years older and more advanced than we are. Our galaxy should be a vibrant, noisy, and crowded place. It should be crisscrossed with the wakes of starships. It should be filled with the chatter of countless civilizations, a great cosmic chorus of information. We should see the signs of their great engineering projects. Dyson spheres built to capture the entire energy output of their stars. But we see none of it. We listen and we hear nothing. The heavens are silent. The paradox is this: all logic suggests the universe should be full of voices, but all observation suggests it is utterly empty. This great silence demands an explanation, and in the context of our journey, in the face of the staggering tower of improbabilities that led to our own existence, the silence leads us to two profound and starkly different conclusions. The first conclusion is that we are simply and truly alone, or, if not alone, then we are the first. This is the essence of the rare Earth hypothesis. It is the idea that the silence is not a mystery, but is the natural state of a universe where the emergence of a world like ours is a near impossibility. In this view, the long and specific list of coincidences that we have explored is not a sign of design, but is in fact the great filter itself. The filter is not a single event, but a long and brutal chain of improbabilities. A planet must have a finely tuned universe with the right laws of physics to even exist. It must then be located in the narrow, safe, and resource-rich habitable zone of its galaxy. It must orbit a stable, long-lived star. It must have a planetary system with a guardian like Jupiter to protect it from constant sterilizing impacts. And then the planet itself must be a miracle. It must have a hot, active core to generate a protective magnetic field. It must have a system of plate tectonics to regulate its climate over billions of years. It must be blessed with a large, stabilizing moon, the product of a cosmically precise collision. It must have the perfect balance of water and land, the perfect atmosphere, the perfect mass, and then, upon this perfect stage, the almost impossible jump from non-living chemistry to the first information-rich, self-replicating cell must occur, and then that life must survive for billions of years and evolve into something complex and then conscious. The rare Earth hypothesis suggests that this chain of requirements is so long and each link so improbable that the chances of all of them occurring in the same place are almost zero. We are not just a 1 in a million shot. We are a 1 in a trillion shot. We are a statistical miracle, a cosmic jackpot. The reason the universe is silent is because we are the only ones, or one of the only ones, to have ever won. If this is true, it places a profound and almost unbearable weight upon our shoulders. It would mean that this small blue world is not just our home, it is the only home that consciousness has ever known in this galaxy. It would mean that all the art, the music, the love, the wonder, the capacity for reason and for understanding exists only here. We would be the sole custodians of meaning in a vast and silent cosmos, the universe's only way of knowing itself. The silence in this view is not a mystery to be solved, it is a responsibility to be carried. It is the sound of our own profound and singular existence. The possibility that we are alone in the cosmos is a staggering and sobering one. It is a conclusion that places the entire weight of cosmic meaning squarely upon our own fragile human shoulders. But there is another way to interpret the great silence and the long, seemingly impossible chain of coincidences that led to our existence. An interpretation that is, in many ways, even more profound. What if the universe is not empty, but is instead quiet? What if the silence is not a sign of absence, but a sign of a deep and patient purpose? This is the other great conclusion that the evidence presents to us. The idea of an intentional design. It is a conclusion that looks at the staggering improbability of our existence and suggests that it is not an accident, but is instead the intended outcome of a system of breathtaking elegance and intelligence. In this view, the universe is not a cosmic lottery that we happen to win. It is a purposefully constructed nursery, and we are its intended occupants. The silence of the universe in this framework is not a mystery to be solved. It is a feature of the design, a profound and necessary one. The silence could be a form of protection, a great cosmic quarantine designed to shield a young, developing consciousness from a universe that is far more complex and perhaps far more dangerous than we can possibly handle. The silence is the sound of the nursery walls, a quiet and protective barrier that allows a new mind to grow in peace, without the overwhelming and perhaps destructive influence of older, vastly more powerful intelligences. The silence could also be a great test, a test of our reason and our spirit, an open and obvious display of a higher power. A constant chorus of voices from the heavens would have made the slow, arduous and character-building journey of scientific discovery and philosophical inquiry entirely unnecessary. We would have been given the answers, but we would never have had the chance to learn how to ask the questions. The silence forces us to figure things out for ourselves. It compels us to build our telescopes, to decode our own genetics, to write our own equations. It is a feature of the design that respects our intellectual and spiritual freedom, allowing us to find our own way to the truth, so that when we arrive, we can understand it, and we can own it. In this grand and elegant view, the emergence of a conscious, comprehending mind is not an accidental byproduct of a random system. It is the goal of the system, the fine-tuning of the cosmos, the privileged placement of our planet, the intricate, information-rich blueprint of life. All of these are not a series of improbable accidents, but the deliberate, layered, and patient brushstrokes of an unimaginably vast and intelligent design. The ultimate purpose of this design, the reason for this great cosmic architecture, is the emergence of a being who can witness it, a mind that can comprehend the physics, that can appreciate the beauty, that can feel awe at the scale of it all. Consciousness is not an accidental passenger in the cosmos. It is the destination. We are the universe's way of knowing itself. We are the part of the cosmos that can look back upon the whole, that can see the intricate web of connections, and that can feel a profound sense of gratitude for the gift of its own existence. And so, the great silence from the stars is no longer a source of loneliness, but an invitation to look closer at the world around us, to understand more deeply, and to appreciate the profound and intricate gift of our own awareness. The Earth in this grand and silent cosmos is not just a random planet. It is a stage, a garden, a sanctuary, and the question of whether it was all a magnificent accident or a deliberate masterpiece is in the end less important than the overwhelming evidence that we are living within a miracle, and we are the ones who get to witness it.